Lesson 10.4 is exponential equations and logarithms. I would pause the video and write down these notes. So a logarithmic function is the inverse of an exponential function. It undoes an exponential function, and basically it solves for the exponent. So if you have an exponential equation, a to the x is equal to b, and you want to figure out what a is, then logarithms were created to solve that problem. So because they're inverses of each other, their inputs and their outputs are switched. So what was originally the input, the independent variable, now becomes the output for your logarithm, and what was originally the output now becomes your input. The base stays the same. So the base of your exponent becomes the base of your logarithm. So if a to the x is equal to b, then x is equal to log base a of b. And this is on your formula booklet. So again, the base a is the base of the log, just like it's the base of the exponential. For this class, you will only need to know base 10 and base e. So if you have f of x to be 10 to the x, then the inverse of that would be log base 10 of x. Input and output switch, base stays the same. The shorthand, because mathematicians are lazy, if we're going to write something a lot of times, we're going to have a shorthand for it, is just to drop the base altogether. So if you have something that is a base 10, you'll often see it written with no base at all. Whenever you see a logarithm with no base at all, you know that it's a base 10 logarithm. If you have f of x equal to our exponential constant e to the x, then its inverse would be log base e of x, and we shorthand log base e as ln. It's called the natural logarithm, or technically in French, it would be log natural, that's why it's ln. So log base e of x, whenever you see this, it's the same thing as seeing ln of x. Whenever you see ln of x, you should automatically know that it's log base e of x. Whenever you're doing logarithms, you kind of always want to keep in your head, it's answering the question, what exponent do I have to raise this base to get whatever numbers inside the logarithm? So what exponent do I have to raise a to get b? It's the exponent of x. So here's a table that we're going to end up completing with exponent and logarithmic forms. So for this first one, we have 10 squared is equal to 100. So if I want to write that in logarithmic form, my base stays the same, so I have log base 10, and my input and my output switch. What was originally my input now becomes my output. What was originally my output now goes inside the logarithm. So for the next one, if I have 10 cubed, well, 10 cubed is equal to 1,000. So then if I want to write this in logarithmic form, I'm going to have log, base stays the same, so it's going to be base 10, and then my input and my output switch. What was originally my output, 1,000, is now going to go inside my logarithm as my input. What was originally my input of 3, an exponent of 3, is now going to be my answer. So I end up with log base 10 of 1,000 is equal to 3, which a lot of times you will see this with the base dropped since it's base 10, and it'll just be written as log of 1,000 is equal to 3. So this is saying 10 to what power is equal to 1,000? Well, it's the third power. Our calculator will calculate log base 10 and log base e. Newer calculators will do base anything, but most standard calculators, anything scientific, will do log base 10 and log base e. So if you're looking at your graphing calculator, log base 10 is what it just says log, right underneath x squared, and underneath that is ln, which is your natural log. So if we want to do this next two, we want to evaluate log base 10 of 10,000. You could probably do it in your head, but if you wanted to do it with your calculator, you would just use log of 10,000. So go ahead and try the next two. Log base 10 of 10,000, evaluate that, and then write that in exponential form. And 10 to the 5th, evaluate that, and write that in logarithmic form. So for log base 10 of 10,000, that's saying 10 to what power would be 10,000? So that would be the fourth power. 10 to the fourth power is 10,000, so that's going to be our logarithmic form. So then if I write this in exponential form, my base stays the same, so this was base 10, so I'm going to have base 10, and then my input and my output switch. What was originally my output of my exponent now becomes my input of my exponent, and then what was originally my input of my logarithm now becomes the output. So I have 10 to the fourth is equal to 10,000. Next one, 10 to the 5th is 100,000, so writing that into logarithmic form, base stays the same, log base 10, which is the same thing as not writing a base at all, input and output switch. What was originally my output now goes inside my logarithm. My exponent, which was originally my input, now becomes my answer. The same thing applies for base e. So if I want e squared, your calculator will do e squared. E to a power is second ln, and then squared. You end up with 7.39. And then if I want to write this in logarithmic form, I'm going to have log, base stays the same, so I'm going to have log base e, and then my input and my output switch was originally my output of 7.39, now goes inside my logarithm. What was originally my input of 2 now becomes my output. And we usually rewrite this as the natural log of 7.39 is equal to 2. So then use your calculator to help you evaluate and write in the alternate form the last three. So for the next one, if I plug this in my calculator, I use the natural log button on my calculator because that's log base e of 20.0386. I end up with an answer of 3. So then writing in the alternate form, base is the same, so base e, input and output switch, my exponent becomes 3 and my output becomes 20.086. Next one, same thing, I plugged in natural log of 54.598 in my calculator and got 4. So then switching forms, base stays the same, input and output switch, e to the fourth is equal to 54.598. Then last one, I just plugged in e to the fifth in my calculator, I got 148.41. So therefore switching forms, log base e, which is the same thing as natural log, of 148.41 is equal to 5. So whenever you want to switch forms, your base stays the same, your input and your output switch. In these examples, we want to solve the equations for x, and we want to use the alternate forms to help us. So use the alternate forms for the first one, use logarithms for the second one, switch out of logarithms, and your calculator to help you evaluate x. Go ahead and pause the video and try these. So for the first one, I need to solve for the exponent, so I want to get it out of exponential form, and I switched it into log form. So base stays the same, base 10, input and output switch, x equals log base 10 of 12, and then I just plugged in log 12 in my calculator and got 1.08. For the next one, I want to get the x out of the logarithm, so I'm going to switch forms into exponential. So base stays the same, natural log is log base e, and then input and output switch. So this says x is equal to e cubed. I plugged that in my calculator and got 20.1. So whenever you want to solve for a variable that's inside whichever form you're in, always switch forms. So if it's inside the exponent, switch into logarithmic form. If it's inside the logarithm, switch into exponential form. In this next example, it says that a disease is spreading according to the model y equals 10 to the t, where t is time in days. We want to find the number of people that are infected initially, so our initial value, calculate how many people are infected after 5 days, and find how long it takes for 3 million people to be infected. For part C, I want us to use logarithms to help us. So go ahead and pause the video and try parts A through C. So for the first one, initial value, that's plugging in 0 for time, so I plugged in 0 for t. You get 10 to the 0 power, which is 1, so 1 person was initially affected. The next one, how many people are infected after 5 days? Again, I plugged in 5 for t and got 10 to the 5th power, or 100,000 people. Part C, find how long it takes for 3 million people to be infected. So I took our function and set it equal to 3 million. And since I'm solving for our exponent here, I want to undo it. So I'm going to switch it into logarithmic form. Base stays the same, log base 10, which is the same thing as not writing a base at all. Input and output switch, so t is equal to log of 3 million. I plugged that in my calculator and got 6.48 days. So given this, go ahead and pause the video and answer the next two questions. How are logarithms related to exponential functions, and what kind of problems can you solve using logarithms? So logarithms, we mentioned in the very beginning, they're the inverses of exponentials. They undo exponential functions, and the kinds of problems that you solve are the ones where you're solving for the unknown exponent. So whenever you want to find your exponent, that's what a logarithm does. It undoes an exponential and gives you your answer, which is whatever the exponent should be. In this last example, it says that the population of a colony of mosquitoes obeys the law of uninhibited growth, that is exponential growth and decay. So it says the population n of the colony over t days is given by the function n of t is equal to n naught e to the 0.6t, where e is our exponential constant e, and n naught, or n sub 0, is whatever our initial population is. Part A says if there are 1,000 mosquitoes initially, what is the size of the colony after 3 days? And part B says how long is it until there are 10,000 mosquitoes? So go ahead and pause the video and try parts A and B. For part A, they tell us that there's 1,000 mosquitoes initially, and n naught represents the initial value, so I plugged that in for n naught in our function. And then I plugged in t to be 3 because they told us 3 days, and then just plugged all that in my calculator. I ended up with 6,049 mosquitoes. Part B says how long until there are 10,000 mosquitoes. So I set up the equation 10,000 is equal to 1,000 e to the 0.6t, which you could very easily solve just using your graphing calculator, but I just wanted to show solving it by hand with logarithms. So the first thing I did is I wanted to isolate the exponential. So I divided both sides by 1,000 and got 10 is equal to e to the 0.6t. And now our unknowns up here in the exponent, so I switched forms. So base stays the same, log base e is the same thing as natural log. Our input now becomes our output, so 0.6t is equal to the natural log of our output comes our input, natural log of 10. And then I want to solve for t, so I divided both sides by 0.6. So you get t is equal to natural log of 10 divided by 0.6, or 3.84 days. And again, I figured this would be continuous because mosquitoes don't just pop up, at midnight every night. So I figured that would be an okay answer for days. So this has been using logarithms to help solve exponential equations and exponential models.